We now want to do a comparison of some of the time-stepping schemes we've developed so far, especially in terms of thinking about the accuracy and stability and the implications of the CFL condition. So the CFL condition actually in practice shows up everywhere you want to deploy these methods. And there's a lot of little rules of thumb that we can start thinking about that I'm going to show you here about how you have to start thinking about what that means. Okay, so the practical considerations. So first of all, it's just time-stepping stability. It is critical that, of course, you're stepping in a stable regime. You're very lucky, by the way, if your instability just leads to blow up. So, for instance, you step along, your scheme's unstable, and your solution goes to infinity. It is often the case, however, that you can generate an instability that makes it look like it's stable. Or it looks like it's not blowing up, but some interesting physics is happening, when it's just simply a numerical artifact. So this stability issue is huge, because if you actually find yourself in a situation where you're actually generating some behavior in your system that looks realistic, but it's just completely due to numerical artifacts, you're in real trouble. So you absolutely have to have a stable scheme. The second thing I'm going to bring up is the idea of what's called numerical stiffness. I'm going to show you some of the things that happen, especially when you have a system with high order spatial derivatives, and it's going to show up directly in our CFL number. And the CFL is going to tell us a lot about numerical stiffness and how much we're going to have to pay for solving some of these codes with higher derivatives. So let's go back to our leapfrog 2-2 using the wave equation as an example. We knew that this was stable for lambdas less than 1. We did our von Neumann analysis. We were able to manipulate the algebra through here and just find that, look, as long as my CFL number is less than 1, then I can go ahead and march this forward stably. Okay. So, but what's it mean for now if we start thinking about leapfrog for the diffusion equation? So let's change it a bit here. We're going to now do not the one-way wave, but the diffusion. Again, diffusion equation. Now I have a second derivative. So here's center difference, second derivative, and now I do basically leapfrog. So I do the center difference in time. And so here's what I get here, and now here's my CFL condition. Now the CFL is the constant c, delta t over delta x squared. Remember, before it's just delta t over delta x. This has huge implications. And I'm going to show you why. Because now, if I want to double my accuracy, here it is, I double my accuracy, that means delta x squared went down by, for the CFL to remain the same, I've also got to take my delta t down by a factor of 4. Because this now gets cut down by a factor of 4, I have to take this down by a factor of 4 to preserve the CFL number. Right? So if there's a CFL condition on this, if I double my accuracy, then I'm going to have to cut my delta t down by a factor of 4. Okay? So this is the implication of the CFL condition. If you double accuracy, which is often what people want to do, you have to cut your time step by a fourth, which means your simulation is essentially going to be 8 times slower because you have double the number of points, plus you have to take steps that are a quarter of the size. So overall, this is what you're actually paying, is that you're saying every time you want to double your accuracy, your code's 8 times slower. All because of this CFL restriction right here. So that's in order to preserve the same CFL number. And typically what you want to do is take a time step just as big as you can. In other words, because you'd like to take the delta t as big as you can in order to solve the solution faster. And so if you want to preserve your CFL number, this is the implications for that. Okay, so let's go ahead and now also consider the Euler method for the heat equation. So here's the Euler method for the heat equation. So I can basically forward difference in time, center difference in space. And by the way, for the forward Euler for the heat equation, what you find is it's stable as long as the CFL number is less than or equal to 1/2. So that sets the restriction for using this method on the heat equation. In other words, you can take, if you pick a delta x, that's going to set what your maximum delta t size has to be. So you notice that See how they're intertwined. The delta x and delta t are not independent. They are, in fact, connected directly through stability. So you have to always keep that in mind, and you have to know where the CFL number is, where the stability boundary is. Okay? Let's go to, and the reason I want to show you the heat equation is I want to go to what's called hyperdiffusion. So it's basically the heat equation, but now with a fourth derivative for the diffusion term. And of course, it's not that much harder, except for now when I do the discretization of the fourth derivative, here's what I get. And notice I have a CFL condition, lambda here. But now notice that the CFL number is delta t over delta x to the fourth. So a second derivative has a delta x squared underneath. A third derivative has a delta x cubed underneath. A fourth derivative has delta x fourth underneath. A sixth derivative has delta x to the sixth underneath. So the higher the derivative, the smaller this is under here. What are the implications of that? Well, let's go through this again. Since there's some CFL condition on which for stability, what we can look at is here is if I want to double the accuracy. So all I want to do is take my grid and I've chopped it up into 100 points, and I want to now chop it into 200 points. So my delta x shrunk by a factor of 2. Then if I double that accuracy, what this tells me for the CFL is now I have to cut my time step down by a factor of 16. So my overall code, since I've doubled the number of points and I've cut it down by a factor of 16, is that it's 32 times slower. So again, you're paying a high price. This is what's called numerical stiffness. Higher derivatives often create this issue that if you want to resolve them, you have to take very, very small time steps. And what it does is it costs you quite a bit to then resolve the behavior well. So, right, 32 times slower. So if your code took, an hour, all of a sudden your code's taking you 32 hours just to double accuracy. So you can see you're not going to want to double accuracy, right? You want to, but of course you would love to have a very accurate solution. So you want to obviously double accuracy, but it's going to cost you a great deal. And so this is something that's really important as a consideration in a lot of these problems is how do you get a code that's not, or an algorithm that's as numerically unstiff as possible. So some general rules of thumb. Whenever you're solving these, what you want to use is adaptive time stepping in order for you to take the largest time step possible. So in fact, in all the ODE solvers that you might encounter, almost every single one has adaptive stepping. And that's exactly the reason they have it, is so that you can take as large a step as possible to march into the future. Okay? Implicit schemes almost always have better CFL conditioning than explicit schemes. So if you're getting into a large-scale problem, what you might want to consider is, are there people who've developed implicit schemes that are actually effective or predictor-corrector schemes, because it allows you to get around a lot of CFL issues and take much bigger time steps. The final thing I'll say is you have to be aware of steppers when you have very strong nonlinear phenomena or rapid changes in your solution. If that's what you have, then that typically is going to represent a numerically stiff problem where it really creates a lot of problems, even for a lot of the adaptive steppers. There's an entire class of steppers built just for stiff problems. It's built into Python, it's built into MATLAB. So anytime you have a problem where you have rapid transition regions, where the solution changes rapidly, that typically is you're typically going to need a stiff solver. And they are there for you to use. They're built into these packages. You should definitely use them, because otherwise what's going to happen in these transition regions, many of the steppers are going to go unstable. And you've seen that it's pretty easy to write an unstable scheme. So it's not like these schemes are just going to be most of the time stable. There's a lot of different phenomena that you're modeling that actually induce instability in the scheme. So just think about that when you're choosing a method overall. And those are, of course, the important choice points you got to start making on a scheme when you're starting to march forward in time. Because if you start choosing unstable schemes, of course, again, you're lucky if it blows up, because then it's announcing itself to you as unstable. What is much more dangerous is you get some phenomena in your code that looks reasonable, but it's just completely due to numerical artifact. And that is the worst thing that can happen to you, because now you're actually making predictions based upon wrong physics. So consider that. So that's the comparison of schemes and thinking about things like numerical stiffness and adaptive stepping.